Hello, it is John Leung speaking to you again. In the first part of this video, I have focused on basic things like where an OLED display is used, introduction to an evaluation kit, where to download the source code, and IDE setup for STM32. In this part, I will tell you how things work from the lowest levels. They are SPI and I2C interfaces. To capture the waveforms, we need a logic analyzer. The ideal place to start is our first program, Hello World. In the source code, we need to find where exactly the first SPI function is called. It is SSD 7317 init. This function is the entry point of the program after system clock initialization. There are few functions with MX prefixes at the beginning, which means they were automatically generated by STM32 templates with parameters fitting requirements of the OLED. Double-click on helloworld.ioc to open the perspective. You may inspect the parameters from the Device Configuration Tool Editor. Expand Connectivity tab. Click SPI1. You will see that the SPI mode is a half-duplex master. Under the SPI tab, there is the full set of parameters. It is an 8-bit data size with the most significant bit sent first, a boot rate set to 16 megabits per second. That is the maximum SPI speed that SSD 7317 can accept. It is difficult to understand the concept without really viewing the waveform. Let's set a breakpoint at SSD 7317 init to see what happens. Click Debug. Click Run to continue. The program will stop at SSD 7317 init. Click F5 to step into it until the cursor reach SPI write command function. Set up the Logic Analyzer software to record. Click Run at SPI write command function. Now you see the SPI waveform with DCS triggered. The first byte received is 7D in hex, followed by 12, AE, and D5. They are exactly the command bytes in the array SSD 7317 init TBL. Look more closely to the waveform. We can see that a command is sent with DC set low. The SPI clock measured to be 16 MHz, with data sending over on a falling edge on DCS. The chip select. Now click F6 on keyboard few more times to step over the functions to proceed. After stepping over the put string function, you will see Hello World displayed on the OLED. How does pixel drawing work? Let's look more closely into the memory layout of the OLED. In SSD 7317 there is a memory region called GDD RAM, which is a bit-mapped static memory holding the bit pattern to be displayed. Our OLED is a monochrome display of 96 x 128 pixels. That means the memory size is only 1536 bytes. This size is equivalent to a memory map of 12 bytes across the width times 128 lines down the display. When we look into the top left corner, we can see that the first 8 pixels is mapped to the first page with the least significant bit first. To display a certain pattern on the first page, we need 2 steps. First, point the memory address to the top left corner. Second, send the byte over with DC set high for data. Staying on the Hello World program, we may demonstrate this concept with a serial terminal program, a shareware. Yet another terminal is used in this demo. In the text box, a preceding /H means hex format. 2100 is to set the line address to the top. 2200 set page address to the left. 7E63 indicates SPI command to send. Click Send Text button. The serial command is interpreted by a function in the main loop, which delegates the SPI write command function with arguments 2100 220 to set pixel position to the top left. Now, let's send over a pattern to draw some pixels. The serial command is 7E64FF, with hexadecimal 64 to indicate SPI data send, and FF is the value to send with SPI write data function. Value hexadecimal FF draw 8 pixels across the top left corner. If you want to draw 16 pixels across the width, change the command argument of hexadecimal 22 to 0 and 1 to span 2 pages. Follow by sending 2 bytes, for example, hexadecimal values FF and 86 with DC set high for SPI data send. In no time, you will see 16 pixels at the top left corner. Let's magnify the pixels to see what is going on. The red label shows the preceding byte hexadecimal FF. With a bit value, 1, displays a white pixel. The blue label shows a pixel pattern of hexadecimal 61. That is not 86. Why? Do you remember how pixels are mapped on GDDRAM? Pixels are mapped with the least significant bit first. But the SPI communication is set to send data in MSB first to fit the orientation of SPI commands of the OLED. When the MCU sends a value of hexadecimal 86 by SPI with DC set high, the bit pattern is mapped to the GDDRAM in a laterally inverted orientation. That is why the second byte is displayed in a pattern like hexadecimal 61 but not 86. That is also why for every character in Hello World, we need to laterally invert the byte orientation. The inversion procedure is not complicated. It is finished in the Reordering tab under Conversion Options of LCD Image Converter, which I have described in the GitHub. By including the font table in the project, the full ASCII character map is now available. That means from the MCU's flash space, we may read the map of H, E, L, L, O to make up the word hello and the second word world. We may read data from flash and send directly with SPI send. With pseudocode looks like this. In this way, we will see each character drawn to the OLED one by one. But if you want to display it in one shot, there is a second way to do it. We don't send directly from flash. Instead, a frame buffer is used to store all characters to MCU's SRAM first. Next, a flag is set to listen to an interrupt event of an FR rising edge. The FR signal is an output generated by the OLED that matches the frame rate. On each pulse of FR, there is the blanking period of display. The MCU is configured to listen to a rising FR pulse that, if there is SRAM data pending to send, data in the area of interest is transferred to GDDRAM with SPI. That is what the local function FBSPI transfer doing. Let's see how the waveform looks in action. Set a breakpoint at the put string function and click debug. The program will halt at the breakpoint. In the Logic Analyzer panel, you will see a continuous pulse on FR. Let's measure the frame rate. It matches with our configuration parameter of 100 Hz. and the blanking period is around 2.4 milliseconds. What it means is that if SPI data flush is synchronized with the blanking period, and flushing can be finished in 2.4 milliseconds, a new frame is updated on the OLED without tearing. It is easy to find out with our setup by setting a trigger on DCS. Zooming in the waveform, we see the first SPI command, hexadecimal 21. It is followed by hexadecimal 22, and a burst of data with DC set high. There is a latency of 14 microseconds, but it is not significant compared to the blanking of 2.4 milliseconds. Zooming further into the data bursts, we can unveil the full content behind. The first command hex21 sets the segment address range. The second command hex22 sets the page address range. The net result forms a rectangle that bounds the area to update, which contains the string, hello world. An image is displayed in a similar way. There are several header files in the project, which I have prepared in LCD image converter. We just need to include them in the project, and make calls to display with a function called SSD 7317 put image. OK, click debug and run. Oops, it plays too fast for naked eyes. We need to add some delay, say 100 milliseconds. Right, it is much better now. Return to the logic analyzer. We need to set a lower sampling frequency to view the FR pulses. The period of FR is 100 Hz, so I think a sampling rate of 500 kHz is good enough. Click the trigger button for few occurrences. Now we see on each occurrence of image display, data flush is synchronized to a rising edge of FR with time fit in the blanking period. The result is a flicker-free image update on the OLED. It is not the end of the story. Now we know that a pixel is displayed with coordinates determined by the intersection of segments and pages, with segments in horizontal and pages that composed of comm lines in vertical. In fact, the segments and comm lines in our in-cell display are more busy than conventional OLED without a touch function. They are continuously driven to sense capacitance fluctuation on the screen surface, so that when a finger lands on it, an interrupt signal is generated. Illustration on this page shows the key map. Touch sensing does not happen all the time. It is triggered in the same FR pulse that we used to synchronize pixel data. On a valid touch event, a pulse is emitted from the IRQ pin. That's why there is a second external interrupt callback function in this place. On the evaluation kit, pin PA12 is assigned to listen to the IRQ pulse. Let's see how touch screen works from another example. The target waveform is an I2C communication, so we need to lower the sampling frequency and change triggering point to the IRQ pin. Click Debug button. You will see the screen is updated with a new interface. Try the touch screen few times. On every touch event, a waveform is captured by the logic analyzer. Zooming in the waveforms, we are able to examine the whole I2C command structure. What is important to us is the touch report of 6 bytes that we can read from the register at the address hexadecimal 0A, F1. On datasheet, a touch report is also called gesture upload data. Another piece of confidential information is shown here. It is tedious to wire up the logic analyzer each time we need to debug the program, so we are calling the remote procedure call function again. It is easier to debug from a serial terminal program. The next task in our program is to decode the data from this list, and respond to it accordingly. With a little bit more imagination, we are now able to create scrolling demo program like this.